Thank you, Fernando, for being here. I'm very happy that you accepted this invitation, and to introduce you. So Fernando Santos is a new member of the IB here at the UVA. He just joined us this month as an assistant professor in the Socially Intelligent Artificial Systems group and the Civic AI Lab. I've had the pleasure of following Fernando's career closely, if I can put it that way. Fernando was until recently a James McDonnell Fellow at Princeton University, and he has been pushing the understanding of dynamic and multi-scale systems. He has won many awards for his PhD in 2018, and he has published extensively during and ever since in extremely high impact fact journals like Nature Sustainability, also in equally competitive conferences on multi-agent systems like the AAAI and AMAS. He even organizes workshops for those conferences, and he has many other activities that you can ask him about afterwards. Indeed, you can ask him about most anything, and he most likely will have thought about it, and he will have something interesting to tell you. So I highly recommend you to do it if you have the chance at some point. For now, he will tell you about some of his work, which is very generally focusing on understanding collective dynamics in multi-agent systems and in designing fair and pro-social AI. So thanks again, Fernando, for accepting this invitation to speak here, and please take it away.
Okay, thank you. Thank you very much. Vitor, can you see my slide, like the presenter's mode or the full screen?
Full screen.
Full screen, okay. Okay, yeah, thanks a lot for the invite, and thanks a lot, Vitor, for the very kind introduction. So I'm Fernando. I recently, as Vitor mentioned, recently joined UVA and Ivy, and I will tell you about information and cooperation in a minute. I had a background slide prepared that Vitor just spoiled, so I'll not take too much time here. I will just tell you that I will be working on models and projects on cooperation and fairness in complex systems, with a particular focus on the impact of AI in social dynamical systems and human society. So yeah, if you believe there's some overlap and some potential collaborations, I'll be very happy to talk with you and just to chat about anything. So I will also be in a joint appointment with ING. So 1 day per week, I will work in fairness and AI. And without further ado, also because I'm the one keeping you away from the sun, and I apologize for that. So in this talk, we will discuss cooperation, and we are going to see that cooperation involves both a paradox and a challenge. We are going to see that cooperation is widespread around us, but it involves a cost. So how come that people cooperate with each other? And we are going to see that this is a challenge. There are many dilemmas, many societal challenges nowadays that to solve them would require some sort of cooperation. What I'm going to do here is in 2 different parts. I will tell you how can information somehow be used to both explain cooperation, but also try to solve some of these cooperation dilemmas. So in the first part, I will tell you about how to use reputations to sustain cooperation. And this is a joint work with Francisco Santos and George Pacheco. And in the second part, I will tell you about biases, about how people sometimes estimate wrongly the behaviors of others in a population, and how these can be detrimental for cooperation. At the same time, I will tell you about how to use information to somehow solve these problems and trigger collective action. And this is a joint work with Vitor himself and with Simon Levine. So cooperation, let me first very briefly tell you what do I mean by cooperation. So if we look around us, we can observe many of these situations where individuals are willing to sacrifice themselves to provide a benefit to others. And the fact that these situations constitute both a paradox and a challenge, as I mentioned, can be easily understood if we resort to this very simple donation game. So let's say that in this game, we have a donor that decides to cooperate or defect with the receiver. So if the donor cooperates, the donor will pay cost C to provide the benefit B. And we assume that the benefits are higher than the costs, which means that in a population, if everyone cooperates, then the overall payoff of this population increases. So it is socially desirable to cooperate. However, because it involves a cost, a defector will always be in a better position than a cooperator. So how can that people cooperate? So this very simple interaction suggests two main questions. Given that cooperation is costly, how can we explain it? And given that cooperation is socially desirable, how can we incentivize individuals to cooperate? And my proposal to answer both of these questions is to use reputations and indirect reciprocity. So indirect reciprocity is the idea that if individuals cooperate today, then others may observe these interactions and they may share information about these interactions in the population, which means which allows others to cooperate back with cooperators in the future. And this is, of course, a very theoretical idea, but in reality, there are some nice experiments pointing out that if people play this simple donation game in the lab, if reputations are provided, then cooperation is able to be maintained in high levels, whereas if reputations are not provided, then cooperation vanishes over time. So there's a link between cooperation and reputations, but to fully understand the connection, we must answer a fundamental question, that is, who should be considered good in a population for cooperation to evolve? So how should we attribute reputations? How should we manage reputations? And this is a very philosophical question in a way, but what we are going to see is that we can also use simulations to answer it. So to answer the question, we have been studying social norms. And here norms are rules that determine how reputations will be attributed. Okay? So let's assume that reputations are binary, good and bad. And now let's assume that an individual A is deciding to cooperate or defect with B. So the next reputation of A that we will represent in this bottom row will depend on the action of A, either cooperate or defect, and on the reputation of B. So we can have one simple norm saying that whoever cooperates will have a good reputation. Or we can be more picky and say that no, only those that cooperate with the good deserve a good reputation. All else is considered bad. So it's easy to see that with this very simple formalism, we can write down 16 possible norms. These are the so-called second-order norms because they rely on two layers of information, a reputation and an action. But in general, norms can use more information. We can, for instance, include information about the current reputation of the donor. Okay? So these will allow us to write judgments such as, if an individual behaves in a certain way, then he or she will be able to maintain his or her reputation. So an extra layer of information, more norms that are possible to formalize. So in general, a norm is this mapping between a set of reputations, one action, to the next reputation of the donor. Oops. So now the challenge is, how can we associate different levels of reputation, different levels of cooperation to different norms? And as I mentioned, we can simulate, and I'm just going to give you some intuition about how we can build these simulations. So we can assume that there's a population where individuals can be either good or bad, and on top of reputations, they can adopt strategies or action rules. So in the simplest scenario, we can have 4 possible strategies. All C, always cooperate. All D, always defect. DISC, that stands for discriminator, so cooperate with the bad, with the good, and defect with the bad. And paradoxical DISC, that is a rather strange strategy of cooperating with the bad and defecting with the good. So then what we do is, from time to time, we select pairs of individuals, and they decide to cooperate or defect with each other based on the reputations that they have and the action rules that they are adopting at any given moment in time. And then after each interaction, there's a new reputation being attributed based on the norm that we fix in the population. Individuals will accumulate payoff, And the final assumption is that strategies will evolve based on this payoff. And the assumption is that those strategies leading to higher levels of payoff will have a higher chance of being imitated. So we assume a model of social learning. We also assume that with some probability, individuals can just randomly explore the strategy space. Now, how can we then study this system? So let's recall that we have 4 strategies, right? So we can organize all the possible states of our population in this 3-dimensional simplex, where the vertices will correspond to the states where everyone adopts the same strategy. Ideally, we would like to study evolution in this all state space, also in that there can be any arbitrary combination of strategies. But this is quite hard to do. It's hard to do because, at least analytically, because we have a large number of states, it's quite hard to write down explicitly a function for the fitness of each individual or the average payoff. And it's equally hard to write down explicitly a function for the distribution of reputations. One possibility is to focus just on the dynamics along the edges of these state space. And this is a well-known approximation called the small mutation approximation. This assumes that most of the time our system will be in one of these monomorphic states where everyone is adopting the same strategy. So this is one possibility. Another one is to simulate. And I'm just going to give you some idea of the type of information that we can extract here. So we can learn about the states in our configuration space where the population will spend most of the time. So here, these spheres correspond to the states where the system will spend more than 80% of the time. So we just order the states in the descending order of the most visited states, and we place one sphere until we cover 80% of the simulation time. So most of the time, the system will be around this edge and also those back edges. Here, color represents reputation. So blue is good, red is bad. So in these states, everyone or almost everyone will be good. And in the purple state, we will have a coexistence of good and bad labels. And by inspecting these cross sections, we can also learn about the most common dynamics that our population will transit to. So with a model like I just want to point out that this is we can extract this type of information, but this is also challenging from the visualization point of view, right? The fact that we have both strategies evolving and also reputation. So I just wanted to give you some intuition for how we are trying to tackle these challenges. So let me give one step back. Let me summarize what we are calculating here. So we are fixing one norm in a population, which means that different strategies will be associated with different reputations, which means that different strategies are going to be more or less adopted based on the reputations that they are associated with and based on the fitness that they have. And the fact that we have different strategies means that we will have completely different levels of cooperation. So in the end, we are able to establish this link between a social norm and the level of cooperation as we intended to. So with a model like this, the first conclusion that we can have, and now for some results, is that not all norms promote equal levels of cooperation. And here we can see that population size, for example, plays a role in the cooperation level under different norms. So here we have on the horizontal axis population size, on the vertical axis cooperation index, which is a fraction of actions that lead to cooperation. And we can see that, and each of these curves corresponds to one social norm. So we can see that for some norms, population size plays an important role. And in general, there is this single norm that was called in the past term judging that is guaranteeing higher levels of cooperation, both in small and in large populations. And this norm is stating that an individual is good if cooperates with the good or defects with the bad. What's interesting is that this norm makes sense from the theoretical point of view, but also in reality, this is a type of moral judgment that is actually used. And there are some really cool experiments with infants where development psychologists try to understand what is the type of judgments that infants do, where it is shown that infants tend to value those that cooperate with the good and defect with the bad somehow. So I don't have much time here, but if you want to know more about these experiments, just ask me later. I'll be happy to tell you more about it. Okay, so now let's stop for a minute and let's reflect a bit on the type of norms and strategies that we are trying to study here. And we should assume that so far norms and strategies are quite simple, right? We are only studying second order norms and strategies that only rely on one bit of information. In reality, of course, we can have individuals that behave with more complex strategies, and norms can use more information to discriminate. And this raises at least two questions. The first one is knowing whether the norms that work well in the context of simple agents and simple strategies will also work well with complex agents and with more complex strategies. And the second question is about how complex is it reasonable for a norm to be and still be argued that it can be used by humans. So we are going to see that if we allow norms to include more information, then we open a Pandora box and we can have norms that are extremely complex. So the question is, how simple can a norm be while still promoting high levels of cooperation in these systems? So to answer or to tackle both of these questions, we studied fourth order norms. So these are norms that additionally include a layer about the previous reputation of an individual. So notice that now, even if we are considering that reputations are binary, now the information associated with an individual is not binary anymore, because now we can distinguish between those that always had a good reputation now and in the previous time step from those that only recently got a good reputation. We have 4 layers of information, so we can write down more than 65,000 norms. And the first conclusion is that if we follow a similar procedure as the one that I presented before, we can realize that there's only a small set of norms promoting very high levels of cooperation. So this is an arbitrary threshold, but if we check the norms that promote more than 90% of cooperation, for example, we can only find 0.2% of all possible norms. Okay, so this is the first key idea. There's only a small set of norms promoting high levels of cooperation. However, we can still distinguish norms within these very restricted set in terms of how complex are these rules. And let me give you an example. So here we have 2 examples of norms, norm 1 and norm 2. And we know that both of these norms promote very high levels of cooperation. However, these norms differ in complexity, and this is not that easy to see if we have norms in this bit string format. But if we translate bits to English, then we can realize that norm 1 has a quite complex judgment. Norm 1 is saying that an individual is good if that individual cooperates with an enduring good, so someone good now and good in the past, or an individual is good and cooperates with someone good, or is bad and effects against someone that is good but was bad in the past, or is good and effects against someone that is bad. So this is a quite complex judgment to have, especially compared with norm 2 that is simply stating that an individual should be good if he or she cooperates with someone good or defects with someone bad. And now the challenge is to quantify this difference in complexity. And for this purpose, we got inspired in a work of 2000 by Jacob Feldman, a mathematical psychologist. And what this author tried to do was to how easy it is for humans to learn Boolean concepts. And there's some limitations with this approach, but one possible solution is to translate the Boolean concept to a logic formula, minimize this logic formula, and count the number of literals. And the less literals the formula has, then the easier it is for people to learn and to apply these concepts. Now, this was a quite complex explanation itself, but let me translate this to the context of our norm. So what we need to do here is to now regard norms not as bit we have been doing, but as logic formulas that when evaluated to true will assign a good reputation. Okay? So we have 4 logic variables, P, S, A, and C. And now we will assume that good is true and bad is false. And likewise, that cooperate is true and that defect is false. And what we need to do is to translate each of the bits where our norm assigns a good reputation to a corresponding logic term. So what we have here, for instance, in this first term, is the idea that an individual should be good if these four variables are true, okay? If P, S, A, and C are true. And for the second bit, we have the idea that an individual is good if P and S are true, and if A and C are false, which corresponds to the second term here. We apply these systematically, we create this full formula, and then we can apply well-known methods to simplify this formula. And then by counting the number of literals in the formula, we can have an heuristic or some quantification of how complex is a norm. So in the example that we had before, we can note that norm 1 can be translated by a formula with 13 literals. Norm 2 can be translated by a formula with 1, 2, 3, 4 literals. So we can say that norm 1 has a complexity of 13 and norm 2 has a complexity of 4. And now we can repeat this to all the plus 65,000 norms that we had before. And the nice thing is that now we can map norms in this two-dimensional space of not only cooperation, but also complexity. And what I am showing you here is that we don't need norms to be extremely complex to promote high levels of cooperation. So what we have here is this curve corresponds to the maximum cooperation that we can obtain with norms with a certain complexity. Okay? So here we have complexity. On the vertical axis, we have cooperation. So for example, here, we have the norms that are extremely simple. For instance, everyone is good or everyone is bad. So these norms have a complexity 0, but they are not very effective, which is natural. Now we can increase complexity a bit. So we can have, for instance, with complexity 1, this very well-known norm called image score that says that cooperation is good, affection is bad. So this is slightly more complex, leads to slightly more cooperation, but we can still do better. We can continue to increase complexity until we reach this level of 4. And then after this complexity, this magical number 4, even if we increase further the complexity of norms, we don't obtain significantly higher gains in terms of cooperation. And the nice thing is that if now we inspect the norms here in this range, norms that promote very high levels of cooperation with minimal complexity, we can again find this norm that promotes nice levels of cooperation in small and large populations, which happens to be the same type of judgment that these infants were doing. And in another perspective, what we are also doing here in a way, and this is, I believe, an idea that can be adapted to other works on evolutionary game theory, in other works reasoning about strategies that humans may or may not use. What we are doing is mapping behaviors in this two-dimensional space of complexity and cooperation. And these can allow us to reason about the norms that are not only cooperative, but that we can affirm that people can use in reality. We can have in other domains, in repeated cooperation dilemmas, for example, we can have strategies that are extremely cooperative, but then in reality, is it reasonable that people will use it? And in another perspective, what we are doing here is playing with different ways of assigning reputation. So if we think about reputation systems and their workings, then this type of methodology can perhaps help us to design reputation systems that are easier to understand for people in a way that are more transparent. And this said, let me now go back to our initial picture and let me now move not only to the second part of the talk, but also to games that are slightly more complex. So now we are going to move from 2-person games to n-person games. Okay. So in these n-person games, and this is a setting that relates very much with this image here, we are going to consider interactions where we need to have a minimum number of cooperators in order to achieve a certain collective goal. Okay, so here, of course, we need a minimum number of cooperators, of people pushing the car forward in order for the car to move. And these are the so-called nonlinear public goods games. And so here I just have one representation of of a game like this, where we have the payoffs of cooperators and defectors as a function of the number of cooperators, we can see that we need, in this example, 4 cooperators to have collective success and to start to have some benefits that scale with cooperation. This is a toy example that applies to the interaction that we had before about pushing cars in the snow. But more importantly, this is also that underlies some of the challenges that today we need to face. If we think about mask wearing, of course, we need to have a critical mass of people wearing masks to protect others around us. Also, if we think about climate change, about reducing emissions, we need to have a critical number of countries to support emission reduction in order to have some impact. So this type of nonlinear public goods dilemmas are quite prevalent and central to solve a lot of the challenges that we need to solve as a society. And one important aspect of these nonlinear public goods is that the way that we reason about the behavior of others, our expectations about the behavior of others may have an impact. So here, for instance, if we know that we are close to the threshold, maybe we feel more tempted to cooperate and to be the one person, the one entity to make the difference. Now, this idea of associating expectations and public goods is not new at all. So this is, I guess, the first paper that studied systematically public goods games in a lab setting. This is a paper from the 70s by Robin Dawes. And one key idea of this paper is already that, and I'm just going to read that, having to make the cooperative or defective choice did affect the estimates of other people, of what other people do, as well as vice versa. So your expectation about the behavior of others is a determinant of your own behavior. And likewise, your own behavior can also impact what you expect from others. So it's not clear what is the causation link, but there's definitely a connection between expectations and behavior. Now, after these, there were many other works, many other experiments replicating this idea. And there's some consensus assuming that, or asserting that people are conditional cooperators. So people tend to cooperate more if they believe that their partners are going to cooperate. And this is one of the stylized facts summarized by Elinor Ostrom in 2000, and that is summarized nicely in this idea that those that believe that others will cooperate are more likely to cooperate themselves. So this is one of the key ideas associated with public goods, let's say. The problem, however, is that we humans, we people, are not that good doing estimates about what others are doing around us. And let me start by telling you about this anecdotal example in a way. So this was a situation that happened in Princeton in the 90s. So what happened was that there was a hurricane and some water treatment facilities were damaged. And as a result, there was a water shortage. Of course, this is a very unfortunate situation. So what the university officials did was to ask students to avoid taking many showers. This is unfortunate, and in the midst of this situation, some psychology graduate students found here a nice opportunity to conduct an experiment. So what they did was to go to dining halls and ask students, first of all, if they were taking showers or not. And second, they asked them to estimate the fraction of colleagues that were taking showers. And these are some results. So what we have here is the estimated percentage of showers as an estimation from those that were taking showers and those that were not taking showers. So what we can see is that there's a difference in the estimate. So people that were taking showers, so defectors in a way, estimated the fraction of defectors to be much higher compared with those that were not taking showers, which is already an interesting insight, right? So your action in a way, well, as was observed in the previous experiments, your behavior is related with the estimates that you do about the behavior of others. What's also interesting is that everyone ended up overestimating the number of defectors. So they were all thinking that there was a higher fraction of people taking showers compared with the real fraction that was 33%. And again, this is a local example. This is a very anecdotal example, but at a global scale, these estimates are likely to play a role in the way that we act in terms of climate change, for example. So this is a very nice cartoon that summarizes this idea, the idea that inside the plane, everyone is thinking that they are the only cooperative people around, and as a result, everyone ends up taking the plane, and people just keep flying and polluting. And these are some really cool experiments or survey where what the authors do is to ask people if they agree or disagree with a certain statement. And again, they ask them to estimate the agreement level in the population. So for example, when they ask in the US, if people agree with this sentence, global warming is caused by human action, then what I found was that people that disagree with the sentence estimate the agreement level to be about 45%. Those that agree with the statement estimate that there's an agreement, a higher agreement of like 55%. Again, the same idea. So your opinion is impacting your estimates. The point, however, is that everyone ends up underestimating how much others agree with these statements. So the real agreement in a population about this sentence is about 75%, so much higher than what people were estimating. So different country, different statement. Now we are in China. The statement is we should sign a treaty that reduces in 90% CO2 emissions by 2050, and same idea. So those that disagree estimate a lower agreement level than those that agree, but overall, everyone ends up underestimating the agreement level in the population. So there's evidence that there are these social perception biases that affect how we estimate that others are acting, or how we estimate that others, how we estimate the beliefs of others. And now the questions that we posed were, first of all, what is the impact of these biases in dynamics of cooperation in public goods claims? And second, how can we trigger cooperation knowing that these biases exist? So the first challenge is how to formalize biases. So what we are doing here is we are calculating a perceived fraction of cooperators that can be different between those that are cooperating and those that are defecting. And this perceived fraction is based on the real fraction x, but then with some correction. So we use this parameter key to control the level of bias by cooperators, and delta will control the level of bias by defectors. So if key and delta are both positive, and what I'm showing here is on the horizontal axis, the real fraction of cooperation in the population. In the vertical axis, we have the perceived fraction of cooperation. If key and delta are both positive, then we are assuming that both cooperators and defectors are overestimating the number of cooperators. So this corresponds to a scenario that's called overtrust. Now, if delta is negative and key is positive, then what we have is that cooperators are estimating a higher number of cooperators than what in reality there is, and defectors are underestimating. So we have this scenario of false consensus. Everyone thinks that their own strategy is more represented in a population than what it actually is. And then we can have the other combinations missing. So we can have undertrust, where everyone underestimates, and we can have false uniqueness, where people think that their own strategy is less represented than what it actually is. And that corresponds to that nice cartoon that we have seen before. So we know how to formalize biases. Now we want to study how are these biases affecting cooperation dynamics. So what we have is a model where there is a certain number of cooperators, K cooperators, and this number of cooperators will vary over time. And our assumption for these dynamics is that individuals are going to best respond to the estimates that they have. Okay. So what's the probability of having one more cooperator? Well, that is the probability of selecting one defector. Okay, so Z is the population size, K is the number of cooperators. So the probability of selecting a defector times the probability that this defector, given the view that he or she has about the world, will best respond and turn into a cooperator. And likewise, the probability of having one less cooperator is the probability of selecting one cooperator times the probability that this cooperator will best respond to the image that he or she has about the world and turn into a defector. So let me now give you some results. Of what we are going to do here is navigate in these biases space in a way. And first, let's see the baseline situation. So what happens if there's no bias? So for this particular game that we are studying, if we don't have any bias, we have a typical coordination dynamics. So this is a situation where if we have a certain critical mass of cooperators, then the population can naturally self-organize to a state where everyone ends up being a cooperator. So what we have here is on the horizontal axis the fraction of cooperators, and on the vertical axis the gradient of selection. So if this gradient is positive, then we expect the number of cooperators to increase. If the gradient is negative, then we expect the number of cooperators to decrease. Okay. So by looking to this gradient, our expectation is that the population will end up in one of these states. So if we have either overtrust or undertrust, the outcome is not that insightful in a way. So we will just move this coordination point either to the right or to the left. So overtrust will move the point to the left. So we need a lower fraction of cooperators in the population for the population to self-organize to cooperation. With undertrust, we move the point to the right. Now, more interesting scenarios appear when we have false uniqueness, for example. So if we have this situation where everyone's strategy is underrepresented in the population, then we introduce a coexistence point here. So we have, in a way, this deadlock situation where we have a critical mass of cooperators that, sorry, we have a coexist, not a critical mass. We have a number of cooperators that keeps cooperating, but that it's perhaps not enough to reach collective success in a lot of groups. Okay, so we are basically wasting resources without achieving the best collective outcome. And if we have false consensus, then we introduce somehow similar type of dynamics. Instead of this prevalent coexistence point, we have this neutral region where everyone will just stick with their own strategies. So no one will change strategies, and so the gradient is 0. So the defectors think that there are a lot of defectors around them, so there's no any benefit in changing to cooperation. Cooperators think that there's a lot of cooperators, so they may just continue cooperating to wait for the collective success that will come. But in the end, everyone will just stick with their own strategies. We can simulate, so we can check that indeed if we perform simulations, and a lot of the simulations end up in these deadlock scenarios where there's some cooperators that are not enough to reach collective success. These are simulations in large populations. If we have smaller populations, then stochastic effects will play a bigger role. And what happens is that these coordination, these different equilibria will not be equally prevalent in a way. And I'm just pointing out this because what I'm going to show you next are some results that look to the stationary distribution of these processes. So in the long run, if we have this noisy, this stochastic process, in the long run, what can we expect in terms of collective success in the population? So let me move to the last plot, and perhaps the most important plot that I'll present here in this part. So what we have here is, as I mentioned, the outcome of or a summary given by the stationary distribution of this stochastic process that I presented before. And this is a summary in terms of group success. Okay. So we will have, what we do is we calculate the probability of having a certain fraction of cooperators. And for this fraction of cooperators, we calculate the group success that we expect for this configuration. And then we weight different configurations given the stationary distribution of the process. And what we have here on the horizontal axis is a phi that we are imposing on the effectors. And this phi is presented in relatively to the costs that cooperators are paying. Okay. So here, of course, in zero, there's no phi at all. And if this parameter is 1, this means that we are imposing a phi on the effectors that is exactly the same as the cost that cooperators need to pay, well, to cooperate. Okay. And so what we are doing here is how, and again, on the vertical axis, we have a measure of group success, so the fraction of groups in the population that will reach collective success. So what we have here is, in a way, a picture that tells us how different populations with different biases may react to incentives. And the first conclusion is, well, quite interesting in my opinion, is that different biases will react very differently to incentives. So for instance, it seems to be easier to guarantee collective success in a population that incurs false consensus compared with false uniqueness. So somehow, and relating to the previous plots that I showed, it seems to be easier to disturb that neutral region than to remove that coexistence point in the false uniqueness scenario. And the second conclusion that I would like to highlight is related with how imposing a phi compares with, for instance, clarifying the real state of the population. So what we have here in this top line is what we have if there were no phi, no bias or no phi in the population. So this is a plot for a setting where, in the absence of bias, individuals in the long run would naturally self-organize to a state where collective success is very high. So, and what I want you to note is that this idyllic scenario is not achieved if we have bias and if we impose a 0.2%, for example. Okay, so this represents in a way a situation where tackling information or tackling the origin of biases can be more effective than providing monetary rewards. And the reason is that tackling these biases is more effective to remove those coexistence points that I showed before. So with fees, it's much harder. We need a much higher fee to remove that that coexistence point. And now for some works that we are still working on together with Vitor, of course. So one thing that we became interested in was to study how these biases will play on networks. So are there any type of networks that can either exacerbate or somehow mitigate the effect of these biases? So this is a joint work with Hughes Neuville, an intern that we were working with at Princeton. And another idea that we are now looking to explore further is the idea of bias heterogeneity. So it's reasonable that in our populations, not everyone has the same bias as the scenarios that I presented before. So if we have different groups possibly being characterized by different biases, what can that say about the way that we build incentives? Should we incentivize different target groups based on the biases that we assume that they have, and so on? And this is also a joint work with Cuttington that was an intern with us at Princeton last year. So this said, let me give you a summary of what we've seen here. So the question that I initially posed was how can information promote cooperation? And in the first part, we have seen that in the context of pairwise interactions and indirect reciprocity, we have seen that there's only a small set of norms that can promote cooperation. We have seen a way of, one out of many possibles that can exist, one way of quantifying the complexity of norms. And these allows us to put in perspective cooperation and also complexity. And in this context, we have seen that simple norms can actually work. But answering directly to that question, the take-home message here would be that information in this context and reputations can be used to highlight justified defections, those that defect with the bad, and also justified cooperations, those that cooperate with the good. So this is the key fingerprint, let's say, of the norm that we found to be highly effective. And in the second part of the talk, we have seen multiplayer games, public goods games, and we have seen some evidence that people often incur social perception biases. These biases are likely to lead to suboptimal deadlocks, so situations where we have this prevalent fraction of cooperators that is not enough to reach collective success overall. Now, reflecting a bit on this, it's actually reasonable that these biases exist. Even so, given the information landscape where we are embedded. So if we assume that we are interacting in networks and that there are network correlations and assortment in the network, then it makes sense that people around to me, and these may lead to false consensus, for example. This can also be amplified by selective exposure to media, for example, and so on. So these biases can be a subjective characteristic of individuals, but they can also be some properties imposed by a certain environment. And again, answering that question, what we have seen here is that information in such contexts can be used to clarify what are the accurate behaviors in the population, and these can trigger collective action. So these, the works that I presented are joint works. The first one with Francisco Santos and Jorge Pacheco in Lisbon and Minho in Portugal. And the second one on bias is a joint work with Simon Levine at Princeton, and also with Vitor here with us today. And that's all. Thanks a lot. And I'm happy to answer your questions.
Thanks, Fernando. We have some few minutes for questions. And while people think of their questions, I guess I can go ahead and ask one. Have you thought of how biases can affect the attributions of social norms?
Yeah.
Of combining these two big projects.
No, that's a good point. I didn't, but that's a nice direction, especially in like these interpretation of norms as descriptive. I think it's descriptive norms, right? That translate the most common behavior. So, and again, thinking about networks, right? That different norms may fixate in different areas of the network, and this may exacerbate these biases. Yeah, that's a cool direction to follow for sure.
Actually, is there any work where the norm, so you attribute being good or bad as just if you're acting the same as the majority of people? So kind of conditioning your reputation on some descriptive norm, as you were saying.
I think there are some at least preprints about the idea of institutional broadcasts, so where reputations are attributed not based on the opinion of a single individual, but as an aggregate of different individuals. So in these were the work that I presented. We are assuming global reputation. So we are assuming that as soon as someone observes the interaction, then they can just spread the word to the whole population. There are some other works with private reputations, and in this context, then people may have conflicting views about individuals. So reputations may result from some type of collective decision process. there are not many works. I think at least there's some preprints about that.
I guess I can go ahead and keep asking questions. Do you see any like application for these kinds of works on the attribution of reputations, like and having different norms for attributing reputations? Well, besides understanding these mechanisms from an evolutionary perspective and so on, but if you think there's some more applied work to business or something.
I think there are some. Well, I think online reputation systems would be the domain where this is probably more easy to apply. It still requires some translation effort, but understanding how. So these second-order norms, for example. So eBay works on top of a very simple reputation system where people are judged based on their action, basically. So these are like first-order norms. But now, if we think about Yelp and TripAdvisor, so what happens if some reviewer that already has a bad reputation, if these reviewer judges the business should this opinion be valued the same way that someone with a good reputation as a reviewer? So there's a direct application in the context of first order reputation systems. I think there's perhaps some also important links with these higher order reputation systems, but online platforms would be probably the most fruitful domain. Yeah.
I see Valentin as a question, and there's also a question in the chat. Valentin, maybe you can go ahead and ask the question.
Yeah, I was wondering, again, talking about applications, whether you could find the analogies to what you were studying and maybe quite simplified problems in the problem we currently have with the many countries reaching the level of vaccination of a certain percent, and then society doesn't move further, and looks like there are certain members of the society who don't want to cooperate. And that really undermines the whole system and the benefits to the whole society of this effort.
No, I agree, Valentin. That's right. I think the reputation systems can work at an international scale. That's definitely a good point. And it happens in vaccine. I mean, vaccine donations between countries definitely, I assume, have a lot of reputation components associated with that. And now that you mentioned, and going back to Vitor's question, also in international climate negotiations, for example, so this pledge mechanism of the Paris Agreement, it builds a lot on reputations, right? The fact that you need to pledge and there's no explicit reward or punishment mechanism. So the assumption is that the reward or punishment will come from indirect reciprocity, in a way, right? From your reputation as a country and how your systems will value your government and so on. So yeah, that's a very good point. I think these types of reputation systems can also play an important role at an international
asking
scale.
On more like individual scale, for example, I come from Russia, and I see that it's really only 10% now of people vaccinated, and it's not more people wanted to get vaccinated. And then this undermines the whole society, right? We cannot reopen, or we are under threat continuously because of the slow level of cooperation and people willing to. Do you think you can transfer your theories to that kind of behavior we observe in this case?
I think at least, well, especially the second part with the biases. So the biases are a potential explanation for why these processes are slow in a way and why people get stuck. I thought about in that specific case of vaccination. I also thought about using that as an example for the non-linear public goods game, but what's not clear for me is like the benefits for the individual, because vaccinating has both a collective benefit, but also you gain immunity. So there's also a benefit for you. So the fact that people are not getting vaccinated probably is due to other like personal beliefs. To relate to that simplified model, I think perhaps we would have to include other opinion dynamics. I don't know, some other type of belief component. But I think the conclusion about the biases and the effect of biases, I think it can translate as an explanation for why some of these processes of having cooperation gaining momentum may be slowed down. Thanks.
Thank you.
Yeah. So we're on time, but we have a couple more questions. Maybe I'll ask the question by Sarah on the chat. Sarah says, Fernando, thank you for a very interesting talk. I was wondering whether there are situations where biases could be to our advantage. And then she says, maybe if you have different underlying game structures, not one where everyone would so easily cooperate. For example, I recently found a study that people overestimate virtuous norms in certain contexts, which could possibly increase cooperation. Just comment on that.
Yeah, I agree completely, Sarah. There are perhaps at least overtrust. So in the game that I showed, overtrust is advantages in the sense that if we think that there are more people cooperating than what it actually are, then it's easier to for everyone to coordinate. So for that particular game, that is an example where overtrust is beneficial. Overtrust can also be detrimental in other contexts. For example, if the number of cooperators, if the benefits do not scale with cooperation, then there are situations where you just need the optimal level to have the societal optimum is to have a very specific number of cooperators, and in those contexts, overtrust to not cooperate when in fact you are required to cooperate. So to summarize, definitely, I think there are situations where, especially overtrust is a type of biases that in a lot of dilemmas can actually be useful. Yeah, and I would love to know more about that study.
Maybe Clelia has disappeared. Hans, you can go first, and then Clelia can come back.
Hi, Fernando. Very cool talk. Can you hear me? Yeah, I think so.
Yes,
right?
yes, I can hear you. Thanks.
I was thinking, and that's probably maybe something you hear relatively often. Isn't your approach a relatively cynical one, given that like cooperation, etc., seems to be a social learning process, or very much determined by what you experienced in the past? And whereas I think of people, for example, that don't seem to learn that bad behavior is bad, or I'm thinking of people that seem to be just very good, but not for reputational reasons, because that would mean that in unseen situations, they're actually very bad. So I want to believe, for example, that somebody like the Pope also anonymously donates to Greenpeace or something like this. So does your approach really rely on cooperation behavior being mostly a learned phenomenon?
Yeah, I mean, I agree that I mean, the cynical part of it, that you only have cooperation if interactions are not anonymous, and that in the end, if you cooperate today, then you get a benefit in the future. This is a key part of that of this model. So one argument to use it like this, and that it's often used, is that okay, today we, even in anonymous settings, we may feel tempted to cooperate. So how can we explain that today, even in anonymous settings, we can feel tempted to cooperate? One justification is that, well, but during most of our evolutionary time, we interacted in the context of small-scale societies where anonymous interactions were actually not that common at all. So I think it's, I mean, understanding how cooperation emerges how cooperation works in the context of anonymous interactions. That's definitely, I mean, that's a fascinating topic. And there are some nice works on the idea of intuitive cooperation and how if you need to think fast, you tend to cooperate more. So somehow cooperation got hard-coded in us. So in a way, perhaps this type of evolutionary models provide a justification for why this became hard-coded and not that much for how in the context of anonymous settings nowadays we can leverage cooperation. Yeah, I mean, that's a very pertinent point.
Yeah, and I totally think your work is great, especially when you like limit the world a little bit to local systems like online marketplaces or something like this, where reputation is so important, and this learning process is very immediate. So yeah, thanks. It was very interesting.
Yeah.
Clelia, last question.
I think, yeah, in that circle, I think that there's the Oscar Wilde, I think it's Oscar Wilde quote that is quite cool, that says that something like anonymous donations are great, especially when people find out about it, something like that. So I think, I mean, just to reinforce that the idea of the fact that this only applies in a way to local interactions with or online platforms where reputations are well known. It's and how to translate this knowledge to anonymous systems. That's a yeah, super important point. Yeah, so thanks. Yeah, clearly, sorry.
Yeah, no problem. It was really interesting, and it's not really my field, so probably I will. I don't know if what I'm going to ask is interesting or not, but I was wondering what happened if, like in the case that you have implemented, people have the same social norm. So you decide for a social norm, and everybody have the same social norm, right? But what happens if your society is very polarized, and then people have different type of social norm? Like, yeah, what happened in that case? Like, if people don't have the same impression of what is good and what is bad, or yeah. Mm-hmm. Have you looked at this?
We played around with some models where we have a coexistence of norms. It's still like in a mean field approach where we don't assume necessarily correlation between like people that use the same norm interacting more often, and we didn't find a combination of norms that would contribute to higher levels of cooperation compared with having a single highly cooperative norm. So one difficulty of studying the dynamics on norms is that it's not clear what's the payoff associated with using a norm, because a norm is being used by those that observe. So you observe the interaction, you assign a reputation, but what is your own benefit, or what are your costs as the norm user? So that's one challenge to study the dynamics on norms, and how we can reach a state where we have a coexistence of norms. But that's I mean that's a cool study to do on networks as well. I mean, if you have some network correlation in terms of norms, you have different regions in a network using different norms. So how will these impact the overall levels of cooperation? I think, yeah, that's a very super interesting way to move forward. Yeah.
All right. Thanks everyone for the questions. Thank you, Fernando, for the great talk. And I guess I'll see everyone next week.
Okay, thank you, Victor, and thanks everyone.